Throughout the development of the E8 cross E8 heterotic quantum gravity framework, a specific rational fraction appears repeatedly. We see the ratio of 1/7 emerge in graviton dynamics, discrete charge structures, and cosmic microwave background predictions. There is a massive scale difference between the subatomic symmetries where this fraction is theorized and the macroscopic, physical Earth where its effects are observed. Traditional theoretical models struggle to explain this recurrence. They treat the 1/7 ratio as a phenomenological fit, often interpreting it as a form of arbitrary substrate jitter. This value is a calculable geometric invariant derived directly from E8 topology. The exact quantum bound dictates the physical limits of macroscopic systems, specifically controlling the relative variance of Earth's 800,000-year climate record. Randomness in fundamental physical systems bears the measurable signature of higher dimensional symmetries. The exceptional Lie algebra E8 contains exactly 240 roots. Within E8, the E7 subalgebra plays a unique role. It is the only embedding that preserves anomaly cancellation while leaving exactly 3 generations of particles. This specific subspace consists of 133 roots. We then identify the E8 Weyl vector, denoted as ρ. This vector acts as the single fixed mass axis for the entire framework, defining the direction of maximal symmetry breaking. To understand how the E7 roots map onto this mass axis, researchers ran Monte Carlo simulations. They generated 1 million random SO7 rotations of the E7 root system. These Haar measure rotations mathematically simulate the random, continuous moduli orientations inherent in the K7 compactification manifold. The simulation calculates the projection of each randomly rotated E7 root onto the fixed Weyl vector. This yields the mean squared cosine of the projection angle. The mean squared projection converges exactly to 1/7. This ratio represents the mathematical equipartition of angular momentum for a 7-dimensional manifold projected onto a 1-dimensional axis. While the theoretical value is exactly 1/7, the empirical mean from the 1 million Monte Carlo trials settles at precisely 0.142738. This histogram plots the distribution of the 1 million rotation trials. By zooming in on the x-axis, we see a microgap between the exact theoretical target of 0.142857 and the observed statistical mean. That gap represents a statistically significant deviation, defined as delta, measuring approximately -1.19 times 10 to the -4th. This deviation occurs because the 133 E7 roots do not fill their 7-dimensional space uniformly. Instead, they cluster along high symmetry directions. Furthermore, the Weyl vector itself is anisotropic. Its components decrease linearly, lacking perfect spherical symmetry. In particle physics, this residual geometric noise establishes the natural scale for CP violation. By multiplying this geometric deviation by the sine squared of the Cabibbo angle, we derive a predicted CKM mixing phase. The geometrically predicted phase is roughly 6.6 times 10 to the -3rd radians. This aligns with the order of magnitude measured empirically in the standard model. The matter-antimatter asymmetry of the universe encodes the irreducible geometric noise generated during E8 to E7 symmetry breaking. This geometric limit propagates directly to the planetary macroscale. Traditional climate models suggest relative variance should range from 30 to 100%. To test this, we look at the Epoca Dome C ice core dataset, which captures a continuous 800,000-year record of Earth's atmospheric carbon dioxide. We compare this with a secondary dataset, the GRIP Deep Ice Core, which tracks beryllium-10 cosmic ray flux over 386,000 years. For the Epoca record, researchers calculated the relative variance by dividing the standard deviation of the carbon dioxide levels by their historical mean. This chart plots the 819,000-year Epoca carbon dioxide data. The fluctuations are restricted by a standard deviation of 28 parts per million by volume. Divided by the mean, the coefficient of variation is 0.1313. Researchers applied the exact same relative variance calculation to the extraterrestrial beryllium-10 cosmic ray dataset. This extraterrestrial data yields a relative variance of 0.1784. Both the terrestrial greenhouse gas records and the incoming cosmic ray fluxes strictly cluster around the geometric invariant of 1/7. This mathematical clustering contradicts the wide unpredictable spread predicted by conventional stochastic climate mechanics. Both terrestrial and extraterrestrial climate indicators appear constrained by this substrate-level criticality, following the variance bounds established in E8 topology. The universal ratio of 1/7 fundamentally bridges the massive gap between quantum matter-antimatter asymmetry and 100 millennia glacial cycles. The E8 framework allows us to calculate observable limits from first principles, reducing the need for phenomenological guesswork. Physical reality, from graviton charges to the temperature sensitivity of our planet, emerges strictly from statistical geometry. This geometry forces us to rethink traditional stochastic models and recognize the strict limits of purely empirical observation. The noise inherent in physical systems reveals the measurable geometry of higher dimensional symmetry breaking.